in with the recording in progress. That's very good. So our next speaker for today will be Michiels, here virtually with us from KU Leuven. Wim is, of course, full professor at the NUMA group and is well known for his work in time delay systems. And I think that will also be partly the topic of today. So the title for this talk is Stability, Robustness Analysis, and Long Order Reduction of Periodic Control Systems with Delay. All right, Wim, the floor is yours.
Yeah, so first of all, thank you very much for the kind invitation. So it's very nice to see that young professors are joining together, that young researchers are coming together and taking this that kind of initiatives. So I encourage that very much. So in my talk, I will start by introducing a class of time periodic delay systems. And I will mainly focus in the talk on systems theoretic properties, stability, H2 norms, the concept of Lyapunov equations, and then I will touch at the end structure preserving model reduction. So I will only talk about basic ideas, and for that I also included a section on basic properties for time invariant time delay systems, just to make a presentation of the concepts quite simple. So central in the methodology is duality in systems theoretic sense and Lyapunov matrices. So let's first start with the class. So we have here linearized problems of this form here. X is the state, you have an input, some type of inhomogeneity in which you can interact with the system. You can also do measurements via an output equation, where you collect particular information about the state. And we have two special features, time periodicity, and we have delays. So there are a lot of applications where this type of problems arise. Among others, when you linearize time invariant systems, of course. But the specific problems where we have collaborated on with application-oriented groups are the following: rotating, cutting, and milling machines in machining. So here you see a sketch below. What's the idea about milling a machine? You want to process a material by scraping away material by rotation. So you basically have here cutters that rotate, and the rotation gives rise to periodic coefficients. And then you also have the delay. Where does this come from? Well, the reaction force on the cutter, it depends on the amount of material that has been scraped away during previous rotations. So you get some type of regenerative effect that's translated in the mathematical model by some delay terms. Another application that's recently started up is about power systems and about control of multi-level modular converters for HVDC, so high voltage direct current transmission. So when you want, for instance, to connect the power grid in the UK and in Europe, then a DC link would be the best solution to avoid bad interference and cascading events. So anyway, a lot of applications, and I will discuss some very basic properties of this type of models from a systems theory perspective. But before coming to that, I will just introduce time invariant delay systems and their basic properties. So for an ODE, to make things clear, so if you want to define a solution, what you need, it's a vector. It's time invariant. So if you know an initial condition, a vector at the initial time, at the initial time, you can define the solution forward in time. Yeah. For a delay equation, what you actually need, it's a function. So at time t, time 0, the derivative depends on x at time minus tau. So you need this point here. And then you continue a bit later, you need x at time a bit later minus the delay tau. So in order to define a solution, you need a function segment from minus tau to 0 in this case. And then under very mild conditions, a forward solution is uniquely defined. And now you arrive at some moment at time t. Again, if you want to define the future, the minimal information you need is again a function x subscript t, a function segment from time t minus tau till t. So if you define intuitively the state as the minimal information you need to determine the future, well, then you see already that we have an infinite dimensional system. Hey, because, okay, this is like a continuous function. And this is in fact related to the fact that we can reformulate a delay system into the form of a standard linear equation, because this thing here, it's a bit strange because on the left-hand side, you get the derivative of a vector, and the right-hand side, it's in fact a functional. So where you use information not only at the current time, but also from the history. So how can we now reformulate the whole thing into a more standard form? Well, the state of your system at some time is in fact visible in a window that you can slide along the solution. So at time 0, the state, it's the blue segment. Okay, at this time, which I indicate, the state, it's a function that's going up and down. At time t1, the state, it's in fact the green piece of the trajectory. So, and then when you bring them all together, to the interval minus the maximum delay and 0, then you get some type of evolution in an infinite dimensional space, where you evolved from the green function to the blue function. And in this way, in fact, we arrive at an standard ODE, but where z of t is now an element of this infinite dimensional function space. And how do we define it? In fact, we take two components. How to say that we make distinction between what we call the head, that corresponds to the state x at the current time t, which belongs to Cn. And we also take a tail, and the tail comes from the history. And now, just to give you an idea about how the operator looks like. So when you move the window, suppose that you're fixed to the window, and you slide the window along a solution. What you see then in the window, you see a segment propagating to the left. And now we look for the incremental effect for the derivative. You have a segment, you move it to the left, you take the difference, and then you divide by the change of time, and then you get a derivative. So the tail is in fact mapped onto the derivative. It's a derivative operator. Now, what's now happening with the head? The head is changing according to the original differential equation, which means in fact that the evolution of the head depends on the value of the head, but also on the past, and the past can be sampled from the tail. And in the domain, of course, we consider all functions where there is continuity between head and tail. Maybe, why do we make this distinction between head and tail? One of the reasons is in fact that we want to have the homogeneity, the input out of the definition of the domain of the operator. And we will give another reason later on. So standard, we have in fact, we can reformulate a delay equation as a standard ODE on an infinite dimensional function space, where operator calgraphic A, it's a derivative operator. And this type of duality, these two formulations have played a major role in all the developments that have been done in the group and also by other people. And it's also translating itself to the frequency domain. And when you look at stability, you have to look at an eigenvalue problem, and you end up with either, okay, a finite dimensional non-linear eigenvalue problem, non-linear due to the exponential, or you have an infinite dimensional linear eigenvalue problem. And of course, in this situation, you can take the best of both worlds. So we have developed many algorithms for large scale problems, and then we typically rely on this representation to the right. What do we do for small problems? We combine both things. You have an operator. You suppose that you want to compute all eigenvalues in some compact set. You discretize the operator, you get a matrix, you compute all eigenvalues of the matrix in that compact set. This is an approximation. but then you can do Newton corrections on that finite dimensional formulation to have full accuracy on the individual eigenvalues. Now, how does that discretization of calligraphic A look like? It's a derivative operator. So a natural approach would be, it's not the only approach, would be to use a spectral discretization. And then a derivative operator, it just turned into a standard differentiation matrix. Yeah. And then, of course, what's in fact happening in it's truncated because on the last row, this was related to the derivative of the head. And the derivative of the head, this is in fact determined by the original differential equation. So it's there, in fact, that all system-specific information has a place. Just to give an example here, this is the typical distribution in green of eigenvalues of a delay equation. Okay, we want to compute all eigenvalues in some half plane to the right of this red line. Then our software, it discretizes the operators. Then you get the blue dots. And then at the end, we make some Newton corrections, which are not visible here. But of course, a critical point is how to select n in such a way that in a given right half plane, you have a very good approximation, but without being too conservative. And for that, in fact, we again use a link between a spectral discretization and a rational approximation of the exponential. In other words, the duality, the two eigenvalue problems, this can also carry over, this carries over also to the level of discretized problems. So, and the message is always, okay, take the best of both worlds. What we also need for what's later on, it's the so-called dual system. Hey, you have a system with an input, U, an output, Y. And here you get the frequency domain representation, the so-called transfer function from input till output. And there are many interpretations of that, but just if you're not familiar with it, one of the interpretations is that this corresponds to the Laplace transform of the impulse response. So what's the impulse response? You assume that the system is in rest, and you take for the input delta function centered at 0. In other words, you just initialize your initial state, your head, at B. Then you look at the evolution at the level of the output, and you get a function g of t, the impulse response. And when you put that in the frequency domain, you get the so-called transfer function. What's now the dual system? This is in fact formulated here, and you get the corresponding transfer function. So in other words, this thing corresponds to taking the complex conjugate transpose at the level of the transfer function, at the level of the non-linear formulation. And much related to that, we can also define a left eigenvector of the primal system as a right eigenvector of the dual system, but corresponding to the complex conjugate of the eigenvalue. An important thing which I want to make clear now, also for later, is the following. Defining the dual system in this way does not correspond to considering the adjoint of operator calligraphic A in the linear formulation. I'm not going to dive into mathematics too much today, but just to give you an idea, suppose that we take here, that we look at the level of the approximation. Calligraphic A, it's approximated by a differentiation matrix where all system-related information is in the last row. Now, if we consider the dual system, we get the same structure, but now the matrices AI are replaced by the transposes of the AI. And you see, of course, that the second matrix cannot be obtained by taking the transpose of the first one. Or to say it in another way, if you would take the transpose of this matrix to the left, then you cannot go back and have an interpretation in terms of a delay equation or an approximation of this. So the dual of calligraphic, the adjoint operator of calligraphic A cannot be interpreted in terms of a delay equation. But we can still have nice connections when we consider duality at the level of the non-linear formulation. And why is this all important? When you have left and right eigenvectors, I think that most of you know that then you can have a nice expression for a derivative of an isolated eigenvalue with respect to some parameters. And this way we have developed many algorithms for shaping the form of a transference function, for shaping the spectrum, for computing pseudospectra or related quantities like pseudospectral abscissa. And everywhere, as one of the components of the algorithms, you need at some point derivatives of eigenvalues, which are given by a formula of this form here. All right, so let's now move a bit to the new stuff, to time periodic systems. Let's first look a bit at stability analysis. Again, stability is determined by the spectrum of an infinite dimensional operator, the monotromy operator. In the previous setting for time invariant system, the operator calligraphic A, this was the infinitesimal generator of the solution operator. But that operator now becomes time dependent. So if you want to have information that takes into account the periodic behavior, then you essentially have to integrate over one period. So if you look at an operator mapping an initial function onto the state at time t with theta period. So it's an infinite dimensional operator mapping a function onto a function. And in this case, you can have two situations. You can have overlap between terminal and initial function, or you can have no overlap. So in the second picture, so when t is smaller than the highest degree, then you get an overlap between initial and terminal function. What's now in fact very interesting, that also in some situations, namely when all delay values and the period are commensurate, which means that they are multiples of one of the same number, in that setting, you can still make connections with non-linear eigenvalue problems. And I'm just going to sketch you the idea for the simplest case when there is one delay equal to the period. So where we're looking for an eigenfunction, I have a function here, I call it phi. Okay, phi here. And I want that phi is mapped by the equation if you integrate over time t onto mu times phi. What do I do now? I now start from some vector phi here at time 0. I just integrate my equation. X dot is a0 times x. So we move on, plus a1 times my x in the past. And because I want to characterize eigenfunctions, I replace x in the past by my current x, the q here, divided by mu. So in this way, in fact, we generate a solution and we determine the initial function based on the evolution of that ODE. So, but to get an eigenfunction at the end, we must have continuity at 0. So if you evolve the equation till the end, okay, then you implicitly define phi via my function over mu, but you must have continuity. So if you take your q at time t, you divide by mu, you must arrive at phi. So for an eigenfunction, a function that is continuous from minus t till t, such that the right part is mu times the left part, it must satisfy m lambda times phi is 0. In other words, we still have a finite dimensional non-linear eigenvalue formulation, which allows us to extend many results from control theory from time invariant to time periodic systems. But there's one big difference, that before the relation was very explicit, and now we get in fact an implicit relation in the sense that to determine m of mu times a vector, you have to solve an ODE. And now, once again, you can really combine the best of both worlds. You can, in fact, Weiss algorithms, which either make use of the second representation or the first one, or combine the best of both worlds. But in the special, so in the case of commensurate relation period, you can still rewrite the eigenvalue problem for the monodromy operator in terms of a finite dimensional but non-linear problem. It's an OTA, and you see that mu appears here also in a non-linear way. And you have to solve it, and also solving the equation creates non-linearity with respect to mu. All right. Okay, what can we now say in terms of stability optimization? Suppose that we want to optimize the spectrum. We want to compute pseudospectra, I don't know what. Then again, we need derivatives of Lagrange multipliers with respect to some parameters. And now we can, again, use the formula which I have sketched before for time invariant systems. But now you see again, we need now a left eigenvector. And now at the non-linear level, it's quite easy. Okay, the left eigenvector is equal to the right eigenvector corresponding to some to the n of mu, where n is the complex conjugate of the non-linear function m. Now you can in fact explicitly work out how do you evaluate your m of mu. Well, now you have to start from some vector v. If you want to define n of mu, this should be mu, n of mu times v. You start now from v. Now you integrate backwards in time till 0, and then you take the value at 0 minus mu times v. And what can we do now? At the level of the non-linear formulation, we have defined a left eigenvector as a right eigenvector from some function n of lambda. Now we can do the whole reasoning, which I did before, in reverse order. Now we can interpret this, linearize this until we get some linear problem for an infinite dimensional operator, which can happily be interpreted in terms of a differential equation, namely this one. In other words, via some way around, via the non-linear formulation, I arrived at the natural dual system is this one. You get like a copy of the system, but you do some type of affine transformation of the arguments. So in general, in fact, we end up with the following. We have a primal system of this form here. For the dual system, we have to switch input and output matrices. The B is replaced by C transpose. The AI are also transposed. Transposed, not complex conjugate transposed, because I assume they map T onto a real matrix. But now you have, in fact, a very, maybe not that intuitive transformation of the arguments, and some type of asynchrony between the argument of the AI of T and the argument of the corresponding C term. So we have now two systems, and what can you now show? The first important property is that both primal and dual system, that they share the same spectra, except for possibly 0. So the spectrum, that also means that in fact stability is carried over in two directions. Now I will talk a bit about the H2 norm. And I don't know to what extent you're familiar with that, so I will also try to keep things a bit simple. But first I need the following, the concept of a Lyapunov matrix. And what is it? You have here your equation on top, the primal equation. And we define first the fundamental matrix. This is in fact a matrix solution with the following initial conditions. At time s, for some s, you have the identity matrix. And before s, you have 0. So you take the solution starting at time s with initial condition, the head is equal to the identity matrix and the tail is equal to 0. And then you just evolve in time. Just a fundamental solution for generalization of the fundamental solution. But now the difference is in fact that because of the periodicity, your k will not only depend on the time t, but also on the starting time s. So I use s for starting time. And you can evolve it. And what's in fact now the nice thing, what's the relation with the impulse response before? If you take your system and you knock it at time s, you reset the initial condition at time s to b with tail equal to 0. Let's now look here. So the impulse response means that okay, we reset the initial condition to b instead of identity matrix, and therefore the impulse response is equal to b. It's now the initial condition at time s. K ts times b is the emanating solution, and with c of t, this gives you what you see at the level of the output. So what's now the Lyapunov matrix associated with some positive semi-definite kernel W, which is also periodic? It depends on two variables, S1 and S2, and you take the integral from minus infinity to infinity of K transpose, starting with describing the fundamental solution starting at time S1, and to the right you get K starting at time S2. So you basically, in the scalar case, you take two shifted copies, shifted by S1 and S2, and then you compute the integral. It looks a bit like a convolution, but it's not a convolution because you shift in the, you don't have any reversal of time in one of the two terms here. And what can be shown, in fact, that this quantity, the function u that depends on two variables, S1 and S2, it satisfies the following properties: some symmetry property, periodicity property, and it also satisfies two advection PDEs, describing propagation in the S1 direction and the S2 direction, and also some algebraic property. And it's in fact that property where maybe you can already see a glimpse of a standard Lyapunov equation for a linear time invariant system. So now I put this thing here in red, the second equation. Why? Because if you take into account all other equations, they in fact uniquely define a solution for a stable system, and then this equation becomes redundant. But anyway, so we define that quantity. And what's now the H2 norm? The H2 norm is something very simple. It's in fact the energy in the impulse response. I take my system and I knock it at time t, it starts moving. You watch the output and you look at the L2 norm of the output. So I knock the system at time s. And then you see here, this is the impulse response, which we discussed before. Starting at time s, it starts to move. And now we're looking at the energy. So we take the integral from minus infinity to infinity of we just take the L2 norm of the impulse response. How much energy is there in the output? And because for the time periodic system, the moment of excitation is important, we average over S. So it's the averaged energy of the impulse response when you excite the system at some time moment. And now I'm just going to work this out. We can substitute the quantity here at two places. And then at the end, just some easy mathematics, you end up with the following characterization for the H2 norm, namely as the square root of the average of the trace of P transpose UP, and U is now evaluated on the diagonal with S1 equal to S2. What's now the dual, the Lyapunov matrix? It's in fact the following. It's just a primal Lyapunov matrix associated with a dual system defined before. And also here you can show that it satisfies some properties, dynamic properties, advection PDEs, symmetry properties, periodicity properties, and some type of algebraic constraints. Algebraic, it's more a delay difference equation. What can we show in fact? primal and dual systems, they not only share the spectrum, except for 0, but they also share the same H2 norm. And so in this way, in fact, we arrive at the following results. With a dual characterization of the H2 norm, okay, in this way, because of the periodicity of the average, that's the 1/t times the integral from 0 to till t. And the second thing, okay, you have so you get an expression in terms of the primal and the dual delay Lyapunov matrix. So for a standard ODE, like below here, with, I forgot to mention the input term BU and the output C times X, you would have this kind of expression, which I'm sure many of you are familiar with. So in other words, you have something similar, but first of all, we have to average because of the periodicity. And second, instead of solving a standard Lyapunov equation, we have to solve a matrix valued, a boundary value problem involving a PDE in evolving in two directions, so with two variables. And when you take the special case, okay, if you just take no delay, then everything disappears, but you end up with a periodic Lyapunov equation at the end, a Lyapunov differential equation. If you put no delay, no periodicity, then the last equation reduces to the standard pair of Lyapunov equations. Then maybe a thing which I forgot before. Okay, for a time invariant system, the LH2 norm also has an interpretation in terms of the L2 norm of the transfer function under assumption of exponential stability. So you have some type of, I think it's Parseval's theorems, you have some type of duality, but of course in time varying case, we cannot talk about the transfer function anymore, but we still have the time domain interpretation. Just to give an example here with the so-called delay-Mathieu equation. So what we plot here with the curve which I indicate now, it's in effect the expression for the energy in the impulse response based on the primal delay Lyapunov matrix. Yeah? And this, the energy of the impulse response of the primal system. And of course, we have a period here equal to 2, which means that the energy, it's a periodic function. Maybe this might remind you a bit about so-called phase response curves. So the energy, it depends on the moment of excitation. Suppose that you're making an intercontinental flight and you want to do something about jet lag, you need to shift your biorhythm and you need to take a, and you wish to use medication for that, like melatonin or such, then the moment when you take the medication, it's important. Also here, the moment where you hit the system will determine the response. And therefore you get some type of periodic function. So now when we look at the second expression based on the dual delay Lyapunov matrix, which means you look at the energy of the impulse response at the level of the dual system, you get something completely different. It's more flat in this situation, but the average values, they are equal to each other. So by that averaging, you get two coherent expressions expressing the standard notion of a pair of primal and dual Lyapunov matrices in relation to the H2 norm. So maybe you can ask yourself, what's the use of working with a primal and dual representation? It's useful in the context of stability optimization. When you want to optimize criteria related to eigenvalues. But it's also useful in the context of also something which is very well known, a balanced truncation. And I will just hint to some possible extension of balanced truncation to this class of systems. And therefore, in fact, so this brings me to the last topic of today, namely structure preserving model reduction. I suppose that you have your system on top, periodic with delays, and we want to reduce it to a smaller problem where, okay, the input and output dimension remain the same, but the dimension of X, you want it to be much smaller. At the end, it's a black box. You have an input, you put an input function in it, you get an output coming out of it. You want to define a new black box with a new input, a new output, and the input-output map should be quite similar. That's what you want. And here we are interested in preserving structure. So I want that the reduced model has the same structure, has also delays, has also periodicity. And if we do that, yeah, a straightforward approach would be just to throw away some state variables or put them to 0, for instance. But then we need in some way to characterize the importance of a state variable. So now take a state variable Q in Rn. And you want now to determine in some way how important is that direction Q. And I call it a pseudo state. Why? Because as I explained to you before, the actual state, it's a function consisting of a head and a tail. So we have some type of inconsistency. And therefore, I modify my definition a bit. So I define as a measure for observability of a pseudo state. So how well is that state connected to the output? I define the following definition here. I take my state Q, pseudo state, I extend the tail, I extend it with 0. And then we look at the corresponding output. And we're looking at the energy in the output. So if this quantity EPO is high, that means in fact that such an initial condition determined by Q is highly visible in the output. Of course, from an input-output perspective, it's also important to know how well a state or a pseudo state is affected by the input. And therefore, we use the following measure. Let me explain it on the figure. We have here time S. And suppose now that I have an input action on the interval S minus TS to S. On that interval, I insert an input. And before that, the system is in rest. And I want to determine an input function U in such a way that your trajectory is steered towards vector Q. Okay, so you're looking for, okay, what's the input energy in L2 sense needed to reach Q? And Q is a pseudo state, and I don't care about the tail here. I'm only interested in what the head is doing. I'm not interested in the tail. And then we take subsequently, we take the limit where you let T of Ts go to minus infinity. So in other words, you say that I have plenty of time. So I'm looking at how much energy what's the minimal amount of energy in the input needed to reach Q. So that's a measure about connection to the input of your state Q. Yeah. And in fact, in another measure of reachability, but I'm not going to elaborate on that, is looking at the observation energy. The observation is by looking at how well the pseudostate Q can be observed in the dual system. So also here, duality provides an easy criterion. What's now in fact very interesting, so if you look at the energy needed to reach Q, this can be expressed in terms of an outer product of Q transpose U times Q. And what's in fact in between, that's precisely the delay, the primal delay Lyapunov matrix evaluated on the diagonal at S and S, with S the time, the starting time in this case. What can also be shown that okay, the energy needed to reach pseudostate Q can be expressed in terms of an outer product with Q on both sides, and where inside you have the pseudo-inverse of the dual Dirac-Lyapunov equation. So in other words, based on that beast of Lyapunov matrices, you can in fact determine how well a pseudostate Q is connected to the input or visible in the output. And again, this quantity depends on S because we have a periodic system. So the output energy depends on the moment of excitation. So if you change S, it might be that the response is totally different. Also, okay, when you want to reach some pseudostate Q, the moment at where you want to reach it, at least modulo the period, plays an important role here. So what can we now later do? We can also, okay, average these two quantities, and we're looking at a measure for reachability and a measure for observability. It's in fact so the reachability measure is in fact the observability measure for the dual system, and you can average them. So what's now here the whole idea about balancing? The idea is that I want to throw away a state which is not important. Suppose now that you have one direction which is very easily reachable by you, which you can easily affect by the input, but which you cannot see at the output. And you have another direction which can barely be affected by the input, but is very well visible in the output. Then it's very difficult to distinguish between what is the most important contribution to the input-output mapping of both of them. And that's in fact where balancing plays a role. So what do we now do at the end? And that's also at a higher level, the methodology is pretty standard. I want to preserve the structure. So I do transformation, not in an infinite dimensional function space, but simply in Rn. And you do something similar to the dual system. And what's the effect of that? The effect of that is that these averaged quantities, that these things here, so it's the average of your U and V on the diagonal, that you can choose the transformation in such a way that they become equal to each other in diagonal. What does it mean that if you have a diagonal form here? That means that if you make an inner product, that every state is equally reachable and observable. And this thing allows you then to make some truncation. And now, so when we achieve this property, then I say that the whole system is called position balanced. And why is this called position balanced? Recall from before that the natural state, it's a function segment with a head and with a tail. And in fact, you can show that if you compute the infinite dimensional Gramians associated with the linear formulation, that what we actually do is that we only balance part of the Gramian related to the head to the part in Rn, which is in fact expected because we tweaked a bit the energy interpretations where we artificially extended the Q with some tail, or where we say that, okay, I don't care about the tail when you reach the value of Q. So this terminology is also very well related to what you do for second order systems. If you have a finite element model with a mass, stiffness, and damping matrix, if you then do a transformation in Rn and not in some linearization, then you cannot balance the full Gramians, but only part of it, the position or the velocity, or maybe a combination of both, but not everything. And why do we do this? Why do we only balance part of the infinite dimensional Gramians? Because we want to preserve the structure. If you would do truncation at the infinite dimensional linear level, then you will end up with a standard ODE. So what's then the whole idea about truncation? I do the transformation in such a way that all these energy-related quantities observability and controllability averaged or equal to each other in diagonal. And then you can make distinction between the important state variables and the less important state variables. And then you can simply truncate your system into a smaller one, where we only take the, in this case, the top 1 blocks corresponding to the higher values in the balanced remains. Just to explain this by means of a very simple example, it's in fact a proof of concept. Because on this topic, I have worked so far only on theoretical developments. And the next step is then together with the application-oriented research groups I talked about to lift this to realistic and large-scale problems. But just to illustrate the concept, I have here an equation, linear time periodic. There are some delays inside. And we compute the gradients related to these two quantities. So the U and the V, we do some averaging, and we get these two matrices at the very end. And now we do the balancing transformation. I transform the state in such a way that with this transformation in such a way that we get at the end, okay, some diagonal that both U, F and V, F become diagonal. And for this equation, we now see in fact that we can do a transformation in Rn in such a way that there's one state variable that contributes significantly more than the other in terms of being connected to the input and being observable at the output level. So that's in fact a good candidate to reduce the model. And what have I done here? I have now truncated the system of the transformation, and I end up with this reduced model here. Okay, it's not model reduction. You go from 2 to 1, but as I told you, it's just a proof of concept. And if we compute the H2 norm, in the way I have explained it before, via the delayed Lyapunov equation, then we see in fact that indeed that the relative error is relatively small. So, and this brings me then to a few conclusions. So I've talked a bit about first developments of system theoretic properties for time periodic systems with delays. For time invariant systems, what's in fact a very big methodological driver behind our work is always exploiting duality between you have a linear representation and a non-linear one, both in the time domain as in the frequency domain. This type of duality still goes up for time varying problems under some conditions, and you can also exploit it. But I have not worked on, not elaborated further on that. The second thing, in fact, the Lyapunov matrices can be generalized. They lead to coherent expressions for the H2 norm, and can also be or useful in the context of generalizations of position balancing and model reduction. And of course, this is preliminary work related to the proof of concept. The next step is then, of course, to go to large scale problems. And of course, the main challenge then would be to solve the PDE governed boundary value problems for the Lyapunov equations. In other words, solving these types of equations efficiently. And these are very difficult problems. Two-dimensional PDE, V is matrix valued. And you can also show that solutions may not always be smooth. So it's a quite difficult and challenging problem. Okay, this brings me to my conclusions, or to the end of my conclusions, I should say. So thank you very much for the invitation. Again, I hope that you enjoyed the talk, and I'm ready to take questions.
Sorry, we cannot hear you from.
Hello?
No, we cannot hear the people in Edinburgh.
Ah, okay, sorry.
Can you hear them? No.
I hoped that you could hear me during my talk.
Yes, I could at least.
We can hear you. Sorry.
Yes. Okay.
Ah,
fine.
okay, perfect. Yeah.
Do we have any questions online? You can raise your hand and or type in the chat. That's the type of questions you have. Sorry, no. Okay. Well, in case there are no questions.
Well, I may have just a question. So, do you think you're gonna do larger scale setting? Like the problem is like the discretization of the PDE. What method would work better, or like the linear algebra phase? What do you think are the more challenging aspects in solving the PDE that you have? Maybe a little of both.
You mean that the challenging aspects in solving the PDE, which I just showed in this one?
Setting.
Yeah, main challenge is that it's very difficult to exploit structures. That's one issue. And the second challenge is the non-smoothness.
Okay. When you say structure, you mean the structure that comes from the discretization, so like the algebraic or like the nonlinear problem you have, or the structure of what?
Yeah. So if you discretize the equation, it's very difficult to have a structure which can be easily exploited.
Okay.
So that's one issue. And the other issue is then in fact that if the delays are not commensurate, then you can have really difficult discontinuities, which are fairly difficult to handle. And just to give you an idea where this comes from, you see that the fundamental matrix, this has a discontinuity at time s at the starting time. And that discontinuity propagates because you have a delay equation. Suppose that you have a delay equal to 1. At time s plus 1, the derivative depends on the function at time s. The function at time s has a discontinuity, so the derivative will be discontinuous at time s plus 1. The second derivative will be discontinuous at time s plus 2. So that k of t, it's not a smooth function.
Mm-hmm.
And that non-smoothness, it propagates onto that function u, as you can see here. So the integral, it does do some smoothing, but not too much.
Okay, thank you.
That's a main challenge, yeah.
We can thank
You're welcome.
Wim again. So we can move on to our